counter reaches the value of a register, the PWM output will toggle. Let's just say, for sake of discussion, from high to low. The PWM counter will continue to increment up to its top count, and then the PWM output will fall low. So essentially, our average resolution is limited by the ratio of the PWM frequency we're switching at to the timer frequency. For sake of discussion, we'll just point out if we were switching at 250 kilohertz, which is pretty typical for the work that we're doing, and we have a microprocessor that has a main clock running at 8 megahertz, we're limited to a 3.1% duty ratio resolution. And here on the right, this is a simulation. No, I'm sorry, this is not a simulation. This is the average duty ratio resolution achieved using the MSP430 and just measuring at every step in average resolution. Now we can improve this average resolution by extending, basically making an average of averages, extending over multiple PWM signals, multiple PWM intervals at differing instantaneous PWM ratios. So basically, if we, let's just say for sake of discussion, we're running at 3.1% duty ratio, and then we move to 6.2% duty ratio, we can achieve an average effective PWM ratio in between those by adjusting the amount of time we spend at either dithering ratio, at either duty ratio. There's a few tongue twisters in this discussion. So basically, by alternating, say for sake of discussion, between 3.1% and 6.2%, we can get an average resolution. If say we're averaging over 20 cycles, we go 10 cycles at each duty ratio, we can get an average of 5.4% or whatever that would be, somewhere in between the two. So on the right here, this is the actual average resolution of the PWM module when we're averaging over 20 cycles. And on the scale of this graph, you can see that it's roughly continuous. And this is at the same 8 megahertz clock frequency, 250 kilohertz PWM signal. So now with that background out of the way, just recap and some motivation for ripple correlation control. I think we all are familiar with what perturb and observe is. Basically, we iteratively search for the maximum power point of the panel, and the direction of our change in duty ratio is determined by the direction of power change that we're experiencing. Now, basically a smart approach to the problem developed by Professor Krein and some of his students here is ripple correlation control, which instead of perturbing the system artificially, as is done in perturb and observe and some other approaches, we're going to actually use the instantaneous ripple that occurs at the input of the converter as the converter switching. So you can imagine as the converter switch is closed, the current flowing into the converter is rising, the voltage on the panel is falling, and then that process, the converse occurs when the switch, in this case the buck converter main switch opens. So by taking precisely timed measurements in that ripple, in the switching ripple, we can converge to the maximum power point of the panel. Ripple correlation control does converge quickly to the maximum power point. Unfortunately, there are some limitations posed by the panel capacitance. Effectively, the phase shift between voltage and current that we rely on for the RCC algorithm to operate is negated at frequencies above about 100 kilohertz. So ripple correlation control will not work in this implementation above 100 kilohertz. Now, this does pose the question: is there another ripple that's inherent in the converter operation that we could use to achieve maximum power point tracking? And if you think back to what I discussed just a few minutes ago, you'll see that a dither, which we use to achieve higher duty ratio resolution, does indeed induce a ripple in the average current and voltage flowing into the converter. So for sake of discussion, we'll say that this high duty ratio is 9.3%. The average current flowing into the converters is rising. The average voltage is falling. What you see here are the individual switching waveforms. Then we move to a low duty ratio, 6.2%. And the average current flowing into the converter falls and average voltage rises. So using this approach, we can basically implement ripple correlation control on an average basis and achieve some of the same benefits that ripple correlation control gives us. So basically, what is ripple correlation control? It's probably pretty fuzzy at this time. Basically, it's a very, very interesting approach based on the IP characteristics of the panel at the maximum power point. If you've ever thought about it, you'll see that the maximum power point of the panel occurs at a location where dPdI is 0. Now, dPdI is not something we typically think about as we're designing circuits and so forth. But if we multiply that by a constant, in this case we'll multiply it by di dt squared, we can break this derivative into a product of two derivatives, which give us information about the location on the IP curve at which we're operating. If we're at some location here less than I prime, and we're increasing the current flowing into the converter, and power is also increasing, we know that the product of those derivatives is greater than 0, and we're operating at some I less than the optimal value. Conversely, if I continues to increase and power falls, this product is negative, and we're operating at I less than I optimal. So we can take the product of these derivatives and use an integral control law to obtain iteratively the optimal duty ratio at which our converter should run. Now, the evaluation of this integral is simplified just by applying the linear approximations that are commonly done in switch power converter assessment. What we're going to do here is we're going to approximate the change in current that occurs from the beginning of our dithering cycle to the time RD/TD, dithering ratio, time of dithering, and we're going to approximate the slope and current as a positive constant. We're going to do the same thing, approximating the slope and average current as a negative constant on the falling edge. And then using the periodicity of the signal, we can simplify that evaluated integral down into this fairly simple, useful formula. Basically, by applying this iteratively, we will arrive at the optimal average duty ratio for the panel. This tells us that we will move towards the optimal average duty ratio by taking our current duty ratio and adding to it the sign of the power difference at P equals RD/TD, the sign of the power difference between P equals RD/TD and P equals 0. So we sample power here at the beginning of our dithering cycle. Then we sample power here at the transition from high to low duty ratio. And the sign of that difference tells us whether we need to increment or decrement our average duty ratio. So in order to verify that this train of thought was correct, I implemented some Plex simulations. What we have here is a 65-watt panel simulator, which is just a voltage-dependent current source that tracks a set of predetermined IV curves from a BP365 solar panel. We feed that through some parasitic elements into our buck converter. We measure voltage and current at the input of the buck converter, and then implement the DDRCC algorithm in C in a controller for the buck converter. The panel is controlled using a separate insulation controller, and effectively just stepped from 100% insulation down to 0 insulation. Here we have some plots of operation above MPP. So there's two ways to look at this problem. The microprocessor sees it as a difference in power at the beginning and the end of the beginning and the midpoint of the dithering cycle. In this case, we see that this product is negative, I'm sorry. We see this product is negative, showing us that we need to decrement our duty ratio. If we look at that from the IP curve, we see that this derivative, or the product of this slope and this slope, are negative, again confirming that we're operating at some I that's higher than the optimal value. Now, if we go to the other side of the maximum power point, the product of the change in P and I with respect to time is greater than 0, i.e. they're both increasing on this interval, and which shows us that we're operating at I less than I optimal. Again, from the perspective of implementation, from the perspective of the microcontroller, the power at the beginning of the dithering cycle, the difference in the power at the beginning of the dithering cycle and the midpoint in the dithering cycle is positive, which showing us that we need to increase our average duty ratio of the converter to reach the maximum power point. Now, when we're operating at maximum power point, the average power flowing into the panel is roughly constant over the interval. This is effectively, we're just kind of bouncing back and forth right here around the maximum power point of the panel as we transition in our duty ratio, and again giving us basically a constant average power. The difference here in this case is effectively 0, and based on the tolerance of the program that we implement, the converter will continue to operate at this average duty ratio until the panel conditions change. So it's not going to search for a higher power output of the panel. And again, this product is roughly 0. If you take panel power, the change in panel power is 0, and again confirming that we're at the optimal value of I. So the tracking simulation is just basically stepping the insulation on the simulated panel module from 100% down to 10% in 10% increments, then allowing this separate C script to track the maximum power point of the panel and to run the buck converter correspondingly. We define efficiency just as the ratio of the average power that we extract from the panel to the maximum power that can be extracted from the model at that insulation level. So these values were obtained separately, just finding this peak for each level of insulation on our simulated panel. Again, and taking that measurement here on the outside of our parasitics. Now, just a practical side note. I mentioned that we use dithering to increase our average PWM ratio, and here's a kind of a breakdown of how that's done. For sake of discussion, I'll just say that we're operating here between 11% and 12% duty ratio, and as we increase the average duty ratio, we spend an increasing amount of time at 12%. So effectively, this is the steps you see here are these steps between 10 and 11, 11 and 12, and so forth and so on. But by changing the amount of time we spend at each value, we're able to linearly increase our average PWM resolution. Now, this is nice between values, but you can see that as we get near 12, we're going to be running at a duty ratio of 12 continuously, which is going to eliminate the ripple that we need to track the maximum power point. So instead of continuing down that path, we're going to move to a three-way procedure in which we dither between 13%, 12%, and 11%, obtain an average resolution of 11%, thus maintaining the ripple that we need for the DDR-CC tracking. In practice, this three-way transition will be spread out a little bit from the junction in both directions, so that we get an average continuous duty ratio. So these are the very theoretical simulations, just basically showing that the approach works mathematically, and one of the real benefits of the simulations, in addition to fulfilling my undergrad thesis requirements, was that this is going to provide some basis on which to judge the hardware implementation that I'm working on now. So in this simulation, again, we stepped our insulation level from 100% down to 10% in 10% increments, and here this is the the maximum power point of the panel model, and this is the average power that we extracted at the output of the panel, input of the buck converter. And as you can see, we're tracking the actual maximum power point very closely. Over here, this is panel power, or power into the converter. And every time we adjust our insulation, obviously the panel power falls. Panel voltage also falls. And then as the converter moves back to the maximum power point of the panel voltage rises back up to the MPP level. And panel current falls in parallel with panel power. So hopefully I've given you a little bit of background, just showing you why Professor Plala, and I think this is a great idea. And basically what we're doing is we're using a really cheap microcontroller running at low speed for low power consumption, and we're achieving good average PWM resolution. We're, in addition to increasing our average PWM resolution, we are applying or instigating a ripple that we can use for ripple correlation control, maximum power point tracking. So essentially combining two problems into one solution. And as I mentioned, the simulation results seem to say that we're headed in the right direction. And so hopefully the hardware will bear similar results in the next couple weeks. So thank you. I wonder if you have any questions and anything I can clarify. There's a lot of repetitive vocab in this discussion, so if you have any ideas on that, I'd appreciate that as well. Okay. Cool deal. Thanks.
Okay, second, and then Bachelor of Applied Science.
Bachelor of Applied Science degree from Toronto.
Oh, thank you.
Got a master's degree here at the University of Illinois in 2011. Ended it.
Can we just do like full screen view, full screen? Yeah. Here. Thank you. Does this work? Yeah. Hello. So today I'm just going to talk a little bit about kind of really preliminary results that I've got from this thing that I've been working on, which is the real-time estimation of power system distribution factors. And just as an outline, we'll start with the introduction and go through the approach that we're using to compute these distribution factors, present some simple case study results, and kind of outline some potential applications that we see for this work, and finish with some concluding remarks. So the motivation behind this work is really the recent blackouts that we've experienced in North America, which include most notably the 2003 North American and 2011 San Diego blackouts. And in both cases, the postmortem investigations revealed that one, there was a lack of situational awareness in the system for the operators to make the proper decisions, the most accurate decisions, because they had limited visibility outside of their control area. And two, that there was a lack of an accurate model. So again, operators weren't able to make the correct decisions because they couldn't operate on a inaccurate model. So currently, I guess, power system studies are heavily reliant on studies that are conducted on a model of the system, which is obtained offline, usually based on the network topology, historical demand patterns in electricity usage, and also equipment maintenance schedules that are known ahead of time as well. So these studies usually result in a power flow solution as well as these things called distribution factors, which linear sensitivity distribution factors, which are used in real time along with online measurements, SCADA measurements, which together they help to determine whether the system is N-1 secure. And these studies aren't ideal because, you know, kind of the two items that I just mentioned, that an accurate model containing up-to-date network information is required, which may not be always available. And these results, even if the network were correct, may not even be applicable because the system evolution may not match any of the operating points that were predicted during these offline studies. And this is actually reflected in the San Diego case, in which operators didn't know that there was, you know, some kind of network change outside of their system. So the state estimator actually gave out the wrong results because there was not enough correct information for them. And at the same time, we have these phaser measurement units that provide high-speed voltage and current measurements that are time synchronized. So we have these snapshots that are very high frequency synchronized measurements from the system. So the objective of this work is to basically estimate these sensitivity factors by exploiting measurements from the PMUs without the use of a mathematical model. So how do we do this? So to begin, we just point to the most basic distribution factor, which is the injection shift factor, ISF. And I'm just going to point you to this right cloud, which the cloud represents, you know, a power system. And basically, the ISF is defined as this quantity here, which the numerator is the real power flow through line L change due to the change in injection at node I, with everything else being 0. So no other injection changes, only the change at node I. What is the effect on the power flow through line L? And it's normalized by the injection amount itself. Yeah. Yeah. Mhm. Right. Yeah. Mhm. So, you know, if we had, if we could measure this numerator as well as this denominator, then we would be done. We would have the ISF. But, you know, while it's conceivable that we can measure the power out of a node with these, with our measurement devices, it's hard to conceive that we can measure the proportion of line flow due to, you know, line flow change due to a particular node. So what we actually have is sort of this left situation where we have injections from various nodes, 2 in this case, but, you know, it could be up to any number of injections, and some net change in the line flow based on all of these nodes, you know, injecting or taking out power. So what we can do is actually write the net flow, net real power change in this line as the sum of all of these contributions from all the nodes in the system from 1 to n. And if we rewrite this, you know, rearrange this, and then plug it into each of these quantities, we get this expression on the second line. So now we have this expression where we can measure all of these quantities, right? We can measure the line flow in any line. We can measure the the injections at each node. And what we can do is actually stack all of these sets of measurements up into this linear system. And so now if we have you know, more measurements than the number of parameters that we're trying to estimate, we have this overdetermined system which fits nicely into the linear least squares estimation problem. And we can solve for these parameters, which end up being the ISFs in an optimization problem. So the key assumptions that we make in this setting is that, first of all, there are noise-like fluctuations in each of these values that we're trying to measure, and that the ISFs are approximately constant through all of these measurements, so that we're not seeing like a giant jump, which would affect the minimization of the least squares. And finally, just a technicality that this matrix here needs to be full column rank. And of course, there are other distribution factors as well. The power transfer distribution factor, which represents the megawatt change in a line based on due to an exchange between two buses in the system. The line outage distribution factor, which represents the change in the megawatt flow of a line due to an outage of another line, and so on. And all of these distribution factors are somehow used in some shape or form in various power system studies. But the good news is that these can all be computed once the ISFs are known. So really, we need to restrict ourselves to estimating the ISFs from the previous slide. And so next we'll just present some case studies results. And to start with that, so basically for the simulations, I made up PMU data by basically creating random fluctuations in power injections into each node. So basically this is the expression that comes out, which these sets of powers are composed of the nominal power injection at each node I, along with two sort of these pseudo-random values that are drawn from a normal distribution, one of which is proportional to the nominal power, and the other one is independent of the nominal power. And for each set of the random power injection data, we compute the power flow solution, and then in turn compute the power flow through the line that we're interested in. So with that, we created sort of this matrix here, and then measured the resulting line flow based on each set of data, and then computed the ISFs from that. So we can show the accuracy of these based on a case study here, the IEEE 14 bus system. And what we have here is we've injected a 1 megawatt quantity here. So on top of whatever it used to be, an extra injection here, and found that the actual flow through each of these lines in the system was, there were these values. And then using a model-based approach, they were these values. And then using our LSE, they ended up being these values through the line. And in summary, we found that the mean error using our LSE method was about an order of magnitude smaller than the model-based method, which is great. But it's kind of, this is sort of not where this method would be most well used, I suppose. Where it would actually shine would be like if there was an outage in the system, but it was undetected by the system operators. And without the system model, we are still able to come up with the correct distribution factors. So in order to simulate that, what we did was take out the line between buses 10 and 11, but pretend that it went undetected by the operators. So the operators are still thinking that they have the old system. And we conduct contingency analysis. And in particular, we look at the contingency of what if the line between 4 and 5 were outaged. And we compare the line outage distribution factors between the quantities obtained from the system model versus what we have from the LSE solution. And just as sort of a sample of the result, what we found was, for example, on this line, from 2 to 3, the actual post-contingency flow was 0.9, and from the model-based result, we found 0.88, and the LSE result told us 0.9. So hypothetically, just as sort of a hypothetical situation, like if the thermal limit on this line had been 0.9, then the original model-based solution wouldn't have told us that there was an overload in that line, whereas the LSE method is able to adapt to this change in the model and still spit out the right warning. In terms of potential applications, obviously contingency analysis, which we've highlighted in the previous slide, and sort of complementary to that would be to determine the optimal redispatch policy in order to avoid the contingency after we've figured out which lines may be overloaded should a contingency occur. And we can see sort of applications in this for this in congestion relief as well, to link it up with the economics and to use the up-to-date distribution factors obtained in real time. Also in model validation, perhaps we can use our estimated distribution factors and compare them to the computed ones to see if there was a difference, or whether we can use that difference to pinpoint exactly where the model might be incorrect. And finally, also in the impact of renewable resource uncertainty on line flows as well, to propagate the uncertainty of an injection from a renewable resource onto the line flows to see if there would be a problem with that. And to conclude, we've basically introduced a method to estimate distribution factors without the use of a mathematical model by taking advantage of real-time measurements obtained online. And the key advantages of this method is obviously we no longer need to rely on system models and the associated accuracy. And it's resilient to unexpected system topology changes as well as operating point changes. And further work in this would be to explore or to come up with ways to ensure accurate estimates in the presence of either corrupted data or availability of a subset of data, which, adaptive estimation comes to mind. Also distributed computation of these distribution factors related in the sense that we might only have local information from neighboring nodes, and also to obtain accurate estimates using fewer rows of data, like basically fewer sets of data across the system, which would increase the responsiveness to system changes. And questions, answers, comments? Okay. Mm-hmm. Well, we're kind of counting on the fact that the noise in the system that's inherent in the system is sort of like, from us flipping light switches or, stuff like that. That's, yeah. But if it's consistently throughout, I don't see why, because we're looking at the difference between two measurements anyway. So if it's a consistently 5% off, then that kind of goes away with it by taking a difference, I guess. At the moment we do, but this is one of the, the future, the corrupted or availability of only a subset. Right now, Mhm. Well, at the moment, using the LSE, you do need all of the, or we can just use sort of a previous, old data or something like that, and hope that it's correct enough or something. Yeah. Yeah, they're just standard deviations. I just made them up. Yeah. Oh, it's like 10% I'm using. Mhm. So I found the injection shift factors and then calculated flows based on that. Mhm. 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 I think this would only be a problem if it doesn't change at all. I think. Mhm. Mhm. Yeah. I, I don't know. It kind of rides on the fact that it should be full column rank. Yeah. Well, presumably you're running this throughout like the entire period of time, so you always have some kind of most recent result. Yeah, some kind of windowing effect, like where we're taking like the past X minutes and then another past X minutes and type of thing. Yeah. 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 Right. So we're riding on the fact that it changes somewhat, throughout time. It doesn't just stay at 5.